coming here from the University of Amsterdam. I think people who've been here a long time know she was an alumnus. She was an undergrad here, and she did a master's degree as well. She got her PhD at the Max Planck Institute for Astrophysics, working with Hank Sprout, where she did a bunch of work on accretion from black holes, neutron stars, some of which is in this talk. And now she's working at University of Amsterdam, doing some accretion and also working on magnetars. So, thanks for coming.
Okay, well, thank you very much. It's a pleasure to be here. So yeah, so as Shane said, I want to present work today that I was doing mostly during my my PhD, but also something that I've been working on more recently, especially the observational applications to what I've been looking at. So the question that I want to address is the question of exactly how a very strong magnetic field in a star like a neutron star interacts with matter around it. And there's a lot of examples of these kind of sources in nature that are quite interesting and show unusual, unexpected properties. So the first evidence that we have, or one of the best evidence that we have of strong stellar magnetic fields that are interacting with matter, is coherent X-ray pulsations from accretion onto accreting neutron stars. So X-ray systems or neutron star systems that are accreting from a companion and show coherent pulsations that indicate that material is being channeled onto a hotspot onto the surface of the star. Another interesting example of this is when you look at these pulsations, especially in the longer period neutron stars, you can actually see them changing. So this is the neutron star source CENX3, and over time, you can see that the frequency of the spin changes quite significantly. So it kind of goes through these kind of a random walk, but then overall it's increasing. So this also indicates, this is an indication that material is interacting with the neutron star in some way to produce this change in spin. One of the other examples, one that I'll be addressing more in my talk, is this very strong rapid variability on timescales of order the viscous timescales in the disk. So these are two sources. This is a young T-Tauri star and a neutron star that showed just very rapid kind of quasi-periodic variability on kind of unexpected timescales for something to be happening to do with the spin of the star. Another potential example is these unusual X-ray bursts that you sometimes see in neutron star accretors as compared with black hole accretors. So this is a neutron star source that went into outburst and then just turned off for a while, for about a month, and then went into outburst again. This is not understood in the conventional picture of how X-ray outbursts work. Finally, on the other end of on main sequence stars, you have these very long rotation periods. So this is in AP stars, which are chemically peculiar A stars that have very strong magnetic fields. So you can see here, this is the surface magnetic field measured from the emission lines that it shows. And it ranges from around a few kilogauss to up to 10 or even 30 kilogauss. And the spin period that you see spans 4 orders of magnitude. So anything up to from a few days to up to 10,000 days, where we can't actually measure. We can't actually detect any rotation from the star at all. So these things all kind of indicate that that the magnetic field of the star, the strong magnetic field of the star, especially when it's interacting with matter, can produce unusual variability or unusual properties. So how do we understand this? Well, first it's useful to understand exactly how material accretes onto a neutron star or a star with a very strong magnetic field. And the critical thing in this problem is an introduction of a length scale, which is the point at which the magnetic field is going to become dynamically important for what's happening to the accretion of the neutron onto the star. So you can imagine this. So if you imagine this kind of scenario like you see here, where you have just spherically symmetric infalling gas that's just free falling onto the surface of onto the strong magnetic field, at some point the symmetry is going to be broken by the fact that you have this magnetic field. And material is going to start to get streamed onto the poles of the star. So you can see that onto the poles of the magnetic field, the density goes much higher, and along the equator, hardly any material is accreted at all. Now, the point at which the magnetic field starts to become dynamically important for the material accreting is called the magnetospheric radius. And one way of estimating this, the one that's conventionally done, is to equate the magnetic pressure from the dipole to the ram pressure of the free-falling material. And so at the point where these two are about similar, so further away from the star, the ram pressure dominates. The material can just fall in easily. And very close to the star, the magnetic field completely dominates the problem. But where these two are similar is where you can estimate, as a kind of rule of thumb, that this is where the field is going to be important for what the star is going to do. So this point is usually referred to as the magnetospheric radius or the Alfvén radius. And if you just have spherically symmetric accretion, you can estimate it by setting this equation, assuming a dipole field and setting these two quantities equal to each other. So you get that the magnetospheric radius scales with the neutron star's magnetic field and the accretion rate. And those are the two variables in the problem. So if the accretion rate goes up, the magnetospheric radius becomes smaller. And if the magnetic field goes up, the radius becomes larger. Now, in this problem, one of the things that gets neglected is the rotation, the relative rotation between the star and the field. Because this problem here doesn't have any rotation in it. This is just spherically symmetrically infalling gas. In an accretion disk, you have differential rotation between the star and the disk. And when you're estimating this quantity, it's useful to ask whether this is going to become important. So how does a strong magnetic field interact with an accretion disk? So this is basically the picture that we think is valid for this system. So this is a kind of schematic diagram of how the star disk coupling is going to evolve. So in the inner circle here represents the star, which is rotating at speed omega 1, and the outer circle here is rotating at a speed omega 2, and it represents the disk. And initially, what you imagine is that the field lines, the magnetic field lines, are coupling the star to the disk very strongly. So the field lines get very firmly anchored in the disk and are coming from the star, so they're obviously tied there. And the field lines provide a link that couple the star and the disk. But the point is that the disk is rotating, in general, the disk will be rotating at a different rate everywhere in the disk because it's Keplerian, and a different rate from the star. So as the two rotate differentially, the field lines are going to start to get stretched, and you get this toroidal component to the field being generated. So this toroidal component is now going to exert a torque. It's a way of transferring angular momentum between the star and the disk, and it's going to exert a torque on the disk. Now, because the magnetosphere is very low density, what actually tends to happen is that the toroidal field can only grow to a certain maximum before the field lines start to become inflated very rapidly here like this, and then eventually become open. So actually, after only about one winding of the disk with respect to the star, the field lines become incredibly stretched and actually wind and connect and sever the connection between the disk and the star. So this is just what I was saying, which I was supposed to be scanning through at the same time. So what does this mean for the connection between the field and the star? Well, in my work, what I've done is I've said, okay, well, this process is going to happen on around a dynamical timescale. So basically, the relative timescale that it takes to rotate the disk once with respect to the star. That sets the timescale for field line opening, and then presumably reconnection will happen on a rather quick timescale. But the point here is that the fact that you have this differential rotation and shearing of the magnetic field is going to overall exert a torque on the star. And we can parameterize that by assuming that there's this parameter eta, which is the generated component of the toroidal field. So on average, you're generating toroidal field by shearing the field, and that there's some coupled region, delta R, so some radial extent over which, on average, the field and the disk are interacting with each other. So that this is the region where you have kind of efficient coupling that could be dynamically evolving, or it could be changing on a dynamical timescale, but on average is going to couple the field and the disk and allow angular momentum exchange between the star and the disk. So basically these two parameters, eta and delta R, are unknowns in our problem, and then mu is the dipole.
So delta R is the distance between the inner and the outer edge of the disk?
Sorry?
Delta R is the distance between the inner and outer edge of the disk?
The delta R is the extent of the coupled region. So actually what happens is that most of the star is going to be completely disconnected from the disk because of this field line opening. So you expect that only some of the star can actually reconnect on any kind of relevant timescale, and therefore this delta R parameter is always going to be less than 1. So actually delta R over R, so the coupled region between the star and the disk divided by the radius of the disk is less than 1. So only the innermost region of the disk is coupled to the star.
Why should this be less than 1 and not less than 2 or less than 3?
Well, it's actually considerably less than 1. So essentially, it's the place where you can actually expect the field lines to reconnect. So this is something that comes from simulations, where you see that that only the innermost parts of the disk can actually tend to reconnect to the star. So the global field topology that you see is something, it tends to be something like this, or at least an idealized case. So in the inner part of the disk, very close to the star, you have the closed magnetosphere, just like in the spherically symmetric problem, where you have open field lines further away from the star. And then there's some small, kind of not very well constrained region in the inner edge of the disk where you have efficient interaction between the star and the disk. So this is the part that's going to actually be acting to exchange angular momentum between the star and the disk. Only the innermost region here. Now, so where is the magnetospheric radius in this problem? Well, one way of estimating where, because you have a rotating disk and a rotating star, where this magnetic field is going to truncate the disk in this case, is to estimate the radius at which the magnetic field is fast enough or is strong enough to enforce co-rotation. So basically, where the magnetic field is strong enough to force the gas to stop rotating in Keplerian orbits and start rotating with the rotation rate of the star is going to be the magnetospheric radius, the innermost radius of the disk. And when you estimate it like this, you get a slightly different scaling relationship between the magnetospheric radius, or with the magnetic field and the accretion rate. And you also get a dependence on the co-rotation radius. And the co-rotation radius is the second important length scale in the problem. So the first important length scale is the location of the inner edge of the disk. The second important length scale is the co-rotation radius, which is the point at which the star's angular speed and the disk's Keplerian speed match. So essentially, at this point, if you have a field line coupling the star and the disk, they're going to co-rotate, and you're never going to get any shear. So these are the two kind of length scales that we set up in the problem, and we've estimated the inner edge of the disk like this. Okay, so how does this kind of match up to what's understood in MHD simulations? Well, it's not really clear. I was just at Princeton on Friday, and I was talking to Jim Stone about this, and there's actually a lot of work that's starting to be done on this, especially when you have a disk that actually has magnetic turbulence in it. The picture is not completely clear yet. In general, it seems these simulations from earlier work, where you had an alpha disk prescription for the accretion disk, sort of works. So here you see a star rotating with a strong stellar field, and here you see the disk. And you can see that there's some kind of dynamical evolution of the disk. You have channeled accretion. You do barely see channeled accretion onto the star. You do see field lines opening like this. But there's still a lot of uncertainties, namely things like how much of a coupling you actually enforce between the disk and the star, how outflows are launched, how strong the outflows would be. If this process launches outflows, how much material are they actually ejecting, how much angular momentum, and also how the stellar field actually will evolve through the disk. So like how the dipole field is going to evolve through the disk. All of these things are not completely resolved by simulations. Yeah.
What's the co-rotation radius in this case?
It's inside. Yeah. So, or no, sorry, it's well outside. So this is rotating. It's rotating slow enough that you would expect to see strong accretion.
So is the co-rotation radius always outside the disk truncation radius in this case?
This is
by definition.
This is my next slide. Okay, so there's two possible disk states because you have exactly this problem. So you don't need to necessarily have, so these two radii don't know about each other. The co-rotation radius, or don't immediately know about each other. The co-rotation radius is just determined by how fast the star spins, and the magnetospheric radius is determined by how strong the magnetic field is and how high the accretion rate is. So you can imagine two scenarios. So the first scenario, the magnetospheric radius is inside the co-rotation radius, so that the disk can easily accrete onto the magnetic field, right? So the material can come in here, it's losing angular momentum, and it can accrete easily onto the star. Now the opposite scenario is also in principle possible, where here the magnetospheric radius is outside the co-rotation radius. And what that means is that on average, angular momentum is being added to the innermost regions of the disk. So you're actually presenting a centrifugal barrier against accretion in this region. And you're going to prevent accretion onto the star. So what happens in this case? Well, one of the things that should happen is that the star should spin down, because this is a way of extracting angular momentum from the star. The star's angular momentum is being added to the inner regions of the disk. The second thing that could happen in principle is that you can expel an outflow. So this interaction is adding energy to the inner part of the disk, and so you could imagine that it's expelled in an outflow. And this is the earliest proposal when people realized that this is what would happen. This is the earliest proposal for what would actually go on in this case. And this is called the propeller solution, because basically the picture is that you have a very rapidly spinning magnetosphere that propels away all of the material that comes in from large radii. Now, the thing about the propeller solution is that it assumes that you really have a very large, you really have a much faster spinning magnetosphere than the inner edge of the disk. So the inner edge of the disk is spinning considerably slower than the magnetosphere. But you can also imagine, so this is the sort of picture of a propelling disk. So basically the star is spinning so fast that it can very efficiently expel all of the material away. In principle, though, you could have a solution that looks more like this, which is where angular momentum is being added to the disk and is preventing it from accreting efficiently onto the star. But the angular momentum and the energy that's being added to the inner parts of the disk is not enough to actually drive an outflow. So rather than expel all of the matter that's coming in from large radii, you instead kind of shore it up, right? Or you create a dam against accretion. So the point here is that most of the gas is not necessarily expelled just because you're in the propeller regime. So this is the kind of starting point for my research. What would happen in this case if you don't have a propeller? So essentially what you have here is an accretion disk without accretion. So this is a very, it turns out that if you imagine that you have a disk solution where you're adding angular momentum at the inner edge of the disk and you have no mass transport through the disk, you can actually derive a different analytic solution for the disk equations, for the diffusive disk equations. And this was realized already a long time ago by Sunyaev and Shakura in their paper in 1977, where they demonstrated this solution. And they called this solution a dead disk because it's essentially unobservable. It's releasing so much, it's not bright enough to be really easily observed, and it's not actually accreting. And so the point of a dead disk is essentially that you have active angular momentum transport, so you could still have turbulence through the disk, but the same rate at which you're extracting angular momentum, or angular momentum is being moved outwards, you're inserting angular momentum through this disk field interaction. And so on average, there's no accretion through the disk. So simply by having a lot of material in the inner edge, you can prevent a propeller solution from ever being formed, because any material, any excess material that gets actually accreted can still be accreted onto the star. But if you think about the case where you have a mismatch, so if you have a dead disk solution with no accretion, so you have the centrifugal barrier like I just presented, but the outer disk doesn't know about it, so it keeps accreting, you can imagine that you end up with cases where you have accretion bursts. So essentially what happens in this case is that the inner part of the disk is prevented from accreting because of the centrifugal barrier, and material continues to come in, and as it piles up, it pushes against the magnetosphere more and more efficiently. I think this is what I'm showing in the next slide. Right, so you have this case exactly that material is building up. And then at some point, there's enough material in the inner part of the disk to push inside the co-rotation radius. And of course, at that point, you don't have a centrifugal barrier anymore. So the centrifugal barrier disappears, and you just accrete all of the matter that you accumulated very efficiently onto the star. So this is essentially a way of getting bursts of accretion, non-steady accretion onto the surface, onto the star. And what I did during my PhD was to develop a diffusive disk code which used this changing inner boundary condition as a parameter and followed these accretion burst cycles. So these are 4 examples here.
Sorry, previously you said the co-rotation radius moves in?
The co-rotation radius, no, the inner edge of the disk moves in.
Okay.
So the co-rotation
radius
stays fixed, but the radius of the inner radius of the disk depends on how much material is in the disk. So so as material piles up, the inner edge of the disk creeps closer and closer to the co-rotation radius.
So it's clear that this happens before any sort of dynamical. I guess you're not interchange unstable or anything like that. So there's reasons to expect that you will be stable towards interchange instabilities, but this is not something that we explicitly looked at. So what I did in my calculations was to assume that this is the kind of starting point
that you can pile up material like this.
But why would you expect the interchange stable? Because the field is precisely aligned in such a way from the start that it would.
Yeah, but it's stable. It's stabilized by the fact that you have differential rotation in the disk. It's somewhat, yeah.
This must be, I mean, they do not, so the Romanovans, they do non-anti-symmetric simulations, right? And I guess they must see this or not see this in their simulations.
Yeah, I think it's not completely clear because it's not completely clear whether it's really possible. So it kind of depends on the starting conditions because you have to set up a disk that starts at a kind of the right accretion rate so that you could actually pile up material like this. And then it's not completely clear that you can actually pile up material, that the dynamical processes that are happening to reconnect the field and the disk, because that's exactly what the uncertainty is. You don't exactly know how the field reconnects to the disk, how easily material can accrete onto the disk. So this is assuming that happens on longer, that on average you're able to store material.
So it's a lot longer time scale.
So it's it's still much longer time scales than they simulate. They see there's some evidence that this is going on in their simulations for the ones that run the longest and where the conditions are appropriate, but it's not resolved. So these are different examples of the bursts that we see. So here, the solid line here is the inner radius of the disk, which evolves in and out of the co-rotation radius. And then opposite to that, you have the accretion rate onto the star. So what you can see is that the material is slowly building up when the inner edge of the disk is outside co-rotation. So the accretion rate on the disk through the disk is very low. And then at some point, you get this critical point where you can start an accretion burst. It accretes for a while and then drops off again. And as you can see, the period for this instability can change a lot, just depending on what you set for the inner edge of what you set for the conditions on the interaction between the magnetic field and the disk. So in the simulations that I was running, I characterized the interaction between the field and the disk in a kind of time-averaged way with two parameters. The first parameter is this delta R, which is the effective coupling region. So I expect that this should be small but not really well-defined. And this is the kind of time-averaged region that couples the start of the field. The time-averaged length scale that has coupling between the star and the disk. The second parameter is this transition parameter. So you have a disk solution out here where you don't expect any accretion whatsoever, this dead disk solution. And then inside the co-rotation radius, you expect to have accretion that isn't inhibited by the centrifugal barrier. So you imagine that around the co-rotation radius, there's some length scale, which is not very well defined, that's going to take you from one solution to the other. So what I was doing in the simulations that I was running is I was parameterizing the disk field interaction like this, and essentially varying these two length scales with respect to each other and with respect to the accretion rate to see when I got unstable solutions. So now I want to kind of tie it to work I've been doing more recently and ask the question, can this mechanism explain observed variability in accreting magnetic stars? So essentially the predictions of this mechanism are that you will have an instability that's maybe somewhat shorter, this figure, somewhat shorter than the viscous timescale in the innermost parts of the disk. So this is the viscous time. This is scaled in units of the viscous timescale at the inner star, at the surface of the star. So you're expecting an instability that's somewhat shorter than the viscous timescale in the inner part of the disk. So that's still much, much longer than the dynamical timescale, the spin rate of the star, and much slower than the timescale for which material accretes from large distances, so like an outburst timescale. And then you expect to see obvious signatures that the accretion rate onto the star is changing. So there's a couple of candidate sources that might show this kind of variability. One of the promising ones from young stars is this candidate source, EX Lupi, which is a T Tauri star that shows very large outbursts every 2 or 3 years. And in particular, in 2008, so every couple of years, it hangs around in kind of 13th magnitude, and then every couple of years, it goes up to 10th or 11th magnitude for a while and drops back down. And this is kind of seen, they have about 60 years worth of data on it, and it's seen very regularly. In 2008, it had an exceptionally large outburst, where it went up to a factor of about 100 increase in luminosity. and had a duration of around, and the outburst lasted for around 300 days, where you saw these kind of quasi-periodic oscillations of a time scale of about a month before it finally dropped off into quiescence. Now, qualitatively, this matches the predictions that we make in our model. So qualitatively, we can, if we match what we expect the viscous time scale in the system to be, and we take something reasonable for the magnetic field, say about a kilogauss for the size of the magnetic field, and a few days for the rotation period of the T-Tauri star, because unfortunately these are both unknown, you get a kind of match. I mean, you can, or you at least can match the variability that you see with the instability that we propose. So it's possible that this might be a mechanism for explaining this variability. Now, this is an active field of research, at least from an observational point of view. And these type of stars, EX Lupi, are being classed as EXORs, as a kind of like younger cousin of the Fu Orionis type objects, which show much larger accretion bursts over much larger timescales. And there's been a suggestion, at least recently, that these could be a kind of extreme example of a sort of more common behavior, that this kind of variability pattern could actually be much more common. And the type of burst that you see, so here's another couple of candidate objects that that show essentially the same behavior as EX Lupi. So this is a kind of active field where people are trying to get more data on exactly what these young stars do.
Do you have observational constraints in the rotation period in any of these?
I'm not sure.
So is it generally expected that they would be in this regime, with sort of where the co-rotation is inside the?
Well, I think if you make you can plausibly argue that that's the case. So if you make a very simple estimate for what the magnetospheric radius is, and you assume that you have a somewhat strong dipolar magnetic field, which is not necessarily true. This is an open debate question. But you assume you have a field that's about a kilogauss and a rotation period of a few days. Then you end up in this kind of regime where these two match roughly.
But in the end, your accretion rate will always slowly drop down. So at some point, you're going to get to that regime rate.
Yes.
As long as your magnetic field would stay constant. Maybe it doesn't.
Mm-hmm. Yeah, you expect that you should eventually, even if you have a kind of a weaker magnetic field, if the accretion rate drops enough, then you should push outside the co-rotation radius. Yeah. Now, what I've actually done more work on recently is this class of accreting millisecond X-ray pulsars, which are very popular in Amsterdam. And just to go over very briefly what they are, these are transient X-ray binaries. So you have a low-mass X-ray binaries. So you have a neutron star that's accreting material from a companion through an accretion disk. And the thing that's interesting about these, and they show a very large range of about 6 orders of magnitude, possibly more in variability, depending on whether they're in outburst or in quiescence. Now, the interesting thing about these objects, The interesting thing about these objects is that they have small but sort of constrained magnetic fields because they show coherent pulsations. So you can actually measure the accretion, or you can measure the spin period of the star because you see coherent pulsations as the hotspot of the neutron star moves through your line of sight. So you see that these have millisecond pulsation periods, and from using that as evidence that they're accreting through a truncated disk and channeling accretion, you can say that the magnetic fields are of order 10 to the 8 to the 10 to the 9 Gauss in order to be truncating the disk in the regime where you see pulsations. Now, it's not really well understood how these pulsations exist. For example, some sources like Aquila X1 show transient pulsations. So this source has gone into outburst many times, and only during one observation have coherent pulsations ever been observed. So it's not completely clear how these pulsations are formed and what exactly this has to do, whether you can still have channeled accretion even when you don't see pulsations. Now, except for the fact that they show coherent pulsations, they otherwise pretty much resemble normal kind of neutron star low-mass X-ray binaries which don't have detected fields. So neutron stars at low luminosity, they kind of have the same spectral and variability properties, which suggests, if you believe that these are truncated, these ones could also be truncated as well. So this principle of disk truncation, even if you don't see direct evidence through coherent pulsations, could be kind of common to this class. Especially, as Martin said, if you have a very low accretion rate, even a weak magnetic field should eventually be able to truncate the accretion flow. So we have a couple of examples that show interesting variability. The first example is the source that I worked on with Alessandro Petruno this year. And this is a source in a globular cluster, NGC 6440 X2. This is a millisecond pulsar that was discovered to show very unusual outburst characteristics. So I think it was discovered in 2008. And then it just started showing these outbursts. So this is the X-ray flux as a function of time from 2 years, around 2 years or so, from August 2009 until November 2011. And it just would kind of go off into outburst for a few days on a recurring time scale of about a month or a couple of months. And it's completely this doesn't really agree with standard pictures. What we think we understand about when neutron stars go into outburst, isn't matched by this kind of a system. The recurrence time is too short and the outburst is too weak to really understand this in the current models that we have. The second thing...
When you say current models, you mean the ones where the whole disk
where the whole disk
stable and accretes?
Yes, so where you have a conventional ionization instability in the disk, it doesn't make sense for this picture. I mean, the outbursts are quite weak. And the recurrence time is really short. Now, the thing is, when this source went into outburst, so in each of these outbursts that's labeled on this diagram, it repeatedly showed this very strong amplitude quasi-periodic oscillation, which you can see here. So this is the X-ray light curve bin to show that you can kind of see this periodicity here. You see it better if you look at the power spectral the power spectrum. But in principle, this could be an example of the instability that I just showed you. So where you here have episodes of accretion, so where the X-ray flux goes on, and then in the interim parts you have where the X-ray flux decreases a lot because you have the disk being stored in the inner part of the accretion disk.
Is that written in seconds?
Yes.
Wow.
Yes. So it's a very, this is,
time scale.
yeah.
Well, back in dynamical time scale, it's a millisecond here.
Yeah, no, it's,
Well, on the pulsar itself, right?
yeah, the
but
pulsar is
that would be
rotating.
the disk too, roughly, right? In this picture, that's naturally the
In the-
rotation rate.
In the inner edge of the disk, the thing should be rotating it around. So this is already much longer. Yeah, so 5 milliseconds is around
So a second is really long.
But what's the
It's
viscous
not
time?
short.
the viscous, I'll get to that. So the viscous time is about 80 seconds, what we calculated, if you assume for a standard
It
disk.
seems very fast compared to the viscous time.
Yes. So it's about a factor of 10% of the viscous time scale, but much longer than the dynamical time scale. Now this QPO, this quasi-periodic oscillation at 1 hertz, is very similar to another quasi-periodic oscillation, also around 1 hertz, that was seen in this other source, SAXJ 1808, which is the most famous, the first neutron star accreting millisecond X-ray pulsar that was ever discovered. And this source kind of undergoes unusual outbursts as well. So what happens here, this is the flux in crabs as a function of days. It went into outbursts like this, and it drops off. And then in the decline phase of the outburst, rather than just kind of go down exponentially, you get these kind of strange reflaring states. So the source just kind of brightens and then drops again. And you see this kind of flaring until finally it drops back into quiescence. And there's a few candidate mechanisms for this flaring, but it's not well understood. The point, though, is that when you see in several observations of subsequent outbursts, whenever you saw the source in these reflaring states, you saw this extremely strong. So here you can see this is, again, count rate as a function of time. And here you can see it even more closely more clearly than in the NGC 6440 case. You can very clearly see this very long, mostly regular, or very sharp, mostly regular variability. So you have the source kind of turns off, almost becomes undetectable, and then you have this very strong flaring. So does this fit with the picture that I was proposing? So you can calculate, you can estimate, if you think you understand how a viscous accretion disk works, you can estimate what the viscous timescale is at the inner edge of the disk. So this is saying, if we assume that the inner edge of the disk is being truncated roughly at the co-rotation radius, so that is where the star and the star and the disk are spinning at the same rate, then it's going to be, the disk is truncated around 50 kilometers in NGC 6440 and 30 kilometers in SAXJ 1808. If you work out what the viscous timescale is for NGC 6440, you get it's around 80 seconds. So the instability that you see is around 1/10 of a viscous timescale, which is exactly the frequency range, or falls well into the frequency range of the observed instability that I saw in my simulations. So qualitatively, the picture works out. the timescale for the variability works out. Now, we make several arguments in our paper that the instability that we see is a result of accretion bursts onto the star. So even if it's not generated by the mechanism that we see, the evidence is very strong that this is really evidence for channeled accretion onto the star. So one of the things is that throughout the entire time when you see the variability, sorry, I'm really hot. When you see the variability, you see channeled pulsation. So you see definitely that accretion continues to be pulsated onto the star. So there's definitely still accreting pulsations. We also make an argument that the coherence, which is a kind of complicated timing property of the data, also is stronger, very strong around the 1 Hertz frequency that we observe. So we kind of suggest several points of evidence that this is really caused by variable accretion onto the surface of the magnetosphere. And one of the candidate mechanism that we propose is the one that I described.
Is the ratio of the viscous timescale to the period important?
No, because I think it's important in the sense that it's much, much longer. So it's maybe like 10 to the 3 or 10 to the 4 times longer. So this is why, this is what motivates the suggestion that this is something to do with the viscous evolution of the disk rather than something happening on a dynamical timescale, because that's much shorter than the instability that you see.
So how does the occurrence of these spasmodic accretion events depend on the accretion rate?
It always occurs around low accretion rates. So around this place where you would expect that you can plausibly make the case that you're kind of around the co-rotation radius of the star, that the inner edge is around the co-rotation radius.
You do have a big range, right? I don't know quite what the axis is, that an average flux or peak flux?
I think this is the average flux. Yeah, but this is a plot of how this is another point that we made in the paper of how the centroid frequency scales with so that's right, the average flux between 2 and 16 keV. So you see it over a range of a factor of about 10 in X-ray flux.
And is that also natural for your model? Because it seems a fairly large, well, I guess it didn't scale with MDOT all that fast, right?
No, it doesn't scale. It doesn't necessarily scale very strongly. I mean, so in the paper, when I actually did this parameter space map, we find the instability over a very large range of parameter space. But in particular, like we see it in this range, but we also see evidence that there's kind of 2 types of instability. So that there's one instability where, like the extreme case that I showed, where the accretion completely turns off, and you build up material, and then you have another accretion burst. But you also get an instability more similar to what you see here, where even in it's just kind of there's a local mismatch between the accretion rate, the mean accretion rate, and the local accretion rate, and so you just kind of get a faster variability at higher accretion rate, and that's what we propose that we're seeing here.
But how does the interval between accretion events as a function of the viscous time of the rotation radius depend on the accretion rate? There must be a fairly strong dependence.
Yeah, of course, yeah.
The rotation rate is sitting way outside the rotation rate. It must take much longer to build up mass.
That's right. So this is more relevant for the second kind of type of accretion event that I was saying. So you can imagine that if the accretion rate drops very low, then it takes a very long time for enough material to build up to drive an accretion burst. So you just have a very quick accretion event, and then it goes back off again. But what we found is that there's also this range of parameters for the instability where the mean accretion rate is much higher, and you just basically have a kind of small oscillation of the inner edge of the disk around the co-rotation radius. So it happens on a much faster time scale, and the disk doesn't ever turn off completely. And that scales less strongly with the mean accretion rate in the disk than this kind of other range of the parameter or the range of the instability where you have these complete turn-off events, where the disk completely turns off when it's in quiescence, like there's no accretion.
Well, what determines that small parameter?
Sorry?
What determines that small
This was set by the 2 parameters that I introduced. So basically the ratio, the average size of the coupled region that couples the disk and the field, and then the transition radius. So it depends. It depends a lot on the transition radius as well. So where you go from a non-accreting solution to an accreting solution, and how quickly you're able to make that transition. like the length scale over which you
So
make
what
that
do you use
transition.
for this particular case? Maybe at least
So
because this seems now actually to be quite different from the simulations that you showed, right? At least what you were trying to explain this. So do you have a similar sort of?
yeah, so this is what I was saying that can be or could potentially be explained by the kind of simulations that I was showing here. So what you can see is that you have so you have strong amplitude variability, but it's still the accretion rate is changing by a factor of a few, not by orders of magnitude.
Oh, okay, I see.
So you have a kind of like, so depending on these two length scales, you get either very long build-ups and short accretion bursts, or kind of more symmetric events. And this is something that comes out of the simulations that we do. Okay. So another thing that could be interesting that I would like to work on that I haven't yet is the way that this kind of disk solution. So this disk solution essentially proposes that at low accretion rates, you're not the amount of material stored in the disk is not proportional to the accretion rate. So in the normal disk solution, the amount of material in the disk always scales with the accretion rate. So that if you have a lower accretion rate, the inner edge of the disk is much further out, and you have much less material in the disk. This solution decouples the accretion rate through the disk and the amount of material in the disk, because essentially now, in order to keep the disk very close to the co-rotation radius, you need to have a lot of material in the disk. So you're always storing quite a lot of material in the inner part of the disk, even when the accretion rate is really, really low. And this is very different from the standard disk solution that you find. So one of the questions that I have is, okay, if this is the valid disk solution, so when accretion drops very low to very, very low rates through the disk, what happens to the other processes that you expect to go on? So one of the things that I've been wondering is this a possible way that you could get these recurrent outbursts on kind of much weaker outbursts on much shorter timescales? So in the conventional ionization instability picture, what happens is that the material gets cleared out of the disk, and so the disk density falls to a very low rate. And then it starts building up again from the donor star. And at some point, enough material has built up that you can ionize hydrogen. And then when you've ionized hydrogen, you increase the opacity and decreases the temperature in the disk, and it very quickly drives another outburst. So essentially, the wait time is that you have to have enough material in the disk to ionize it again. In this idea, you should have to wait less long before you would get another outburst, because even in quiescence, even if you're able to drive the disk into quiescence, you already are storing more material there to drive another outburst. So this might be a way of shortening the time scale for subsequent outbursts.
So the mass is being stored. I mean, I guess I'm picturing mass piling up on the inner edge, but I guess that's not necessarily.
Yeah. So what I'm saying is that the solution where you get mass piling up on the inner edge, you can extend that over the entire disk. So if you just imagine that the accretion rate through the entire disk is very, very low, then the disk solution that you're going to tend towards is different from the standard one. So you just have, for the same accretion rate, you have much more material in your disk.
Large mass reservoir out to large radii where
Yes, this would be the idea.
Although presumably it's all ionized, where the magnetospheric radius is playing a role, because if that's not ionized.
Yeah. So it's more that the picture that I have, which might not be correct, but the picture that I have is basically that the disk and field are interacting in this way. They're changing the structure of the disk, and this means that the inner part of the disk is talking to the outer part of the disk. So basically, the interaction between the star and the magnetic field is changing the structure of the entire disk.
You don't actually need the ionization; doesn't necessarily play a role.
Well, it plays a role in driving outbursts. I mean, or this is the idea that it drives out. This is what drives outbursts.
So the disk has to get neutral, and then but still has left a lot more than you normally would
Yeah.
say.
So that it requires less to, again, ionize. Now, another question that you can ask, which I will do in the last couple of minutes, is to ask, well, what happens? Say you have this disk solution. What's going to happen to the evolution of the star over a long time scale? So I'm saying, what would happen if you have a disk where there's no accretion, but you have quite a large disk? Well, if you have a propeller in this scenario, when you have a propeller mechanism, as the accretion rate decreases, the disk is more and more efficiently expelled. So you just expect that the disk is going to be completely evacuated. But the point is that in a dead disk solution, the inner disk stays very close to the co-rotation radius, so it can act as an efficient sink for angular momentum from the star. And so in principle, you could spin down the star indefinitely. So this is something that I looked at again with Hank in my PhD, and we found that the important time scale here is the ratio of the viscous and the spin down time scales. So basically how quickly you can transport angular momentum through the disk versus how easy it is to spin down the disk, or spin down the star, tells you whether you can efficiently spin down a star with this mechanism. So there's a couple of things that set the efficiency of the disk. So one of them, or efficiency of the spin down, one of them is the size of the disk. So if you imagine that you have a disk around an isolated star, so you just have an accretion disk, what I'm essentially saying is that the star's angular momentum is being transferred into the disk. So depending on how big your disk is, this process is going to be more or less efficient. So if you have a very small disk, what happens is the inner radius is just going to move of the disk. As you're adding angular momentum to it, the inner radius is just going to move very quickly outwards, and the star isn't going to be spun down. Whereas if you have a very large disk, then the disk essentially acts as a reservoir for angular momentum, and you can very efficiently spin down the star. I'll change this. Okay. So could this explain what's going on, for example, in AP stars? So in AP stars, you have this observation that you roughly very strong magnetic fields have very long rotation periods. So you have to understand how these stars spin down to such long rotation periods. So this is something that when we investigated it, in principle, with a residual accretion disk, you can spin down a star to a period of maybe 10 years or so. To 100,000 years is kind of hard. But to 10 years is possible with this mechanism. Now, an interesting thing that I learned in Russia this summer, is that now there's new observations by Gauthier Matisse, who's kind of the expert, I think, the leading person who investigates magnetic stars. And one of the things that he finds is that all of the slowest rotators, all of the slowest rotating AP stars that he finds are all in binary systems. Sorry? Yes. Yeah. Yes. Yes, that's right. Yes, so that's possibly too large. But I mean, in principle.
They can't be spectroscopic.
No, but I mean, in principle, the point is that if you have a binary system, the binary orbit could act as a sink for angular momentum that you transport from the star. So in this case, what I'm proposing, or what could be possibly happening, is that the disk acts as a conduit for angular momentum exchange from the star to the orbit of the binary. And this explains how you get such very long spin periods. And also this distribution, because if you don't have a large enough disk, or you don't have a reservoir for the angular momentum that you're losing, then the star isn't going to be able to spin down very efficiently. So in the last couple of minutes, this is kind of increasingly speculative, but this can also be very relevant for the study of radiatively inefficient flows, which we think happen in a lot of different kinds of sources, including black hole binaries at very low accretion rates. So this is an old idea, fairly old idea, that at low accretion rates, so at high accretion rates, you have a thin Shakura-Sunyaev type thin disk where that dominates the spectrum. But at low accretion rates, you see a very different X-ray spectrum. You see a very hard power law spectrum with a sharp cutoff. And this has been interpreted that the inner parts of the disk are completely transformed into a radiatively inefficient flow that has very different properties from a standard thin disk. So if you believe the picture where a neutron star has a very hard surface because it has a boundary, but it also has a magnetic field which truncates the disk, exactly the point where you expect to see most of the radiation from a radiatively inefficient flow is going to be exactly where the magnetic field interferes with the flow. So in principle, observations of strong magnetic fields or neutron stars at low accretion rates where you know that there's a magnetic field can be used to test models for radiatively inefficient flows. So this works basically, so if you imagine that, so this is the schematic picture here where the inner parts of the disk are completely transformed into this very puffy, optically thin region called a RIAF, or an ADAF is the same kind of specific case of this. Now, in a disk, the luminosity scales, or the flux in the disk scales like this with the accretion rate over r cubed, which means that if the inner edge of the accretion disk, so most of the luminosity in an accretion disk always comes from the innermost regions closest to the black hole or the neutron star. But if that is a moving surface because you have a magnetospheric radius, then the flux coming from the disk, or the accretion flow itself, is going to scale much more steeply with the accretion rate. So as the accretion rate drops, the flux from the disk should become less and less important. In contrast, the flux onto the star should scale with the accretion rate only, because as long as you're dumping as much material as you're dumping onto the star, that energy has to come out, because you have this very hard surface in a neutron star. So for the same accretion rate, especially if you have a disk that's truncated by the magnetic field, you expect that these sources should be much dimmer than thin disks. And another interesting point is that these types of sources, or these types of flows, rather, are barely bound. So it's very easy to evacuate material from them. It's very easy to drive an outflow in this type of solution. So this might be a way of driving a very strong propeller. So for the same accretion rate, where you might have a thin disk, you would expect, if you had the same solution with a radiatively inefficient flow, you would expect to have a strong propeller. So essentially, the argument is that you shouldn't expect to see sources like this, which are quiescent neutron stars. So one of the observations about neutron stars that contrasts them from black holes is that you often see this type of quiescent luminosity that's maybe 6 orders of magnitude smaller than what you see when they're in outburst, or strongest outburst. So the question is, how do you continue to get accretion onto the surface of the magnetic field, onto the surface of the neutron star, if you have quite a strong magnetic field? And why is the luminosity here, or why is the luminosity in these accretion when you have this kind of X-ray spectrum similar to what you see in black holes?
The argument that this accretion is that it's variable, I guess.
Yeah, it's variable.
The neutron star itself.
No, and then it's very variable, and then it also the spectrum is quite different from what you would expect. So you have a very hard X-ray spectrum still. So there's still evidence of accretion. So one of the things that we concluded in this paper, so I worked on this paper with some people in Detroit, Federico Bernardini, was that at least for SENX4, so at least in this particular example, an ADAF type solution in particular, so this is a solution where most of the accretion energy gets advected through the disk or through the flow and ends up onto the surface of the star. An accretion, this type of flow is essentially impossible to explain this type of observation. So essentially in order to see luminosity that's this dim, for the conditions that you would expect for an ADAF flow, you would require a much stronger field and very high rotation rate than we see. So you would expect to see evidence of disk truncation that you don't see. So, conclusions. The first conclusion, I think, is the one that I wanted to make the most strongly, which is essentially that even if the inner edge of the accretion disk is truncated somewhat outside the co-rotation radius in a strongly magnetized star, it doesn't mean that you necessarily have to have a propeller kind of solution. It doesn't mean that all of the material in the accretion flow is being evacuated. You might be able to get solutions like this, where you don't actually see accretion. Or you can get accretion onto the star even though the accretion rate is very low. Now, I gave you several examples that might be candidates for the disk instability and might be manifestations of this type of disk solution. And I've suggested kind of beginnings of ways anyway that these types of sources, especially at low luminosity, might be able to be used to constrain the types of the actual disk solutions that we see there. That's it.
Could you go back one second? So in this case, so if it's not a ADAF, what's giving you the hard X-rays, or the X-rays that you see?
So I think the picture would be that most of the emission is coming from the surface, from the material onto the surface of the neutron star. I mean, if the disk is being truncated around the co-rotation radius, then anyway more of the luminosity is coming from the surface of the star. So then you still have to explain why you're able to see such hard X-ray luminosity from the surface of the neutron star when you don't see the neutron star very strongly. I mean, I think that this spectrum is fit with a thermal component and a hard X-ray component, but it's not really. I mean, you have an optically thin flow that's just not. It doesn't have to be an ADAF to get a hard X-rays, but I don't think it's clear what the solution would be.